video, we will try to solve the problem given using Pspice, and we will prove that the measured value is accurate or closer to the computed values for this certain problem. So as we can see, we are given a problem which is a current of 5 sine 2 pi 60t enters an element. Sketch the instantaneous power and determine the average power absorbed by the load element when the element is a 5 ohm resistor, a 10 or a 10B or a 10 millihenry inductor, and C a 12-volt source. And there's a give specification that the current into the positive terminal. So first, we try to measure this using this circuit when the element is a 5 ohm resistor first. So first we create a circuit. So now I already created the circuit. As we can see, it composed of a current source and a resistor which is 5 ohms. So now, as we can see, to add this like the before, use place Pspice component for the current source, go to source and current sources and sign. And for the resistor, just click this resistor. And for the ground, just press G. And for the parameters, click this part, which is usually 1K by default, and replace it with 5. Then click OK. Since in our circuit, there is no phase, so the I off is 0, and and then click OK. And then the amplitude given is 5, since the problem stated 5 sine, which is 5 is the maximum current or the peak current. So we will put 5 and then click OK. And for the frequency is 60. So since the given problem is 2 pi 60, which the 60 represents the frequency of the current source. So since everything is set, so to see the simulation profile, we will see the edit simulation profile. As we can see, our runtime is 16.67 milliseconds. So if we solve this by using the formula for frequency, which is 1 over time. So to get the period will become 1 over the frequency, and 1 over the frequency is equals to 16.67 milliseconds. So now we have a maximum step size of 10 seconds, which represents the interval. Then click OK. And now we are going to simulate our circuit. So now so we will add the trees. So first we will cover the instantaneous power. So right click, then add trees. So click the WR1, which represents the power across R1. Then click OK. As we can see, it forms a beautiful a sine wave. So now, to get the instantaneous speed, let's put our point first onto the peak. So now, as we can see, I think this is the peak. So now, for the previous measurement of the peak, so we can see that the power which is in the y-axis is 124.99 with the time of 14.17 4.1735 milliseconds. So if I adjust it here, so there, so it changes depends on the time. So earlier we already measured it, and by substituting it with, since the earlier measurement is 4.1633 m, so as we can see, the formula is P is equals to I squared times R. By substituting it, we can produce the instantaneous power of 125 sine squared 2 pi 60t times 5 watts. Substitute t with the measured time. Earlier, it is measured by 4.1663 m. It produces the power of 124.999 watts, which is exactly the same with earlier with the 4.1735 milliseconds. And for 4.1429 milliseconds, the power produced is 124.999 or 990, which is closer to the computed power here when it is measured at its peak. Since the points are small, we cannot exactly position 4.1633 milliseconds on this graph. So as we can see, the graph produces a correct formula. Formu- the formula the graph proves that the formula used earlier is correct. Now, we will try to measure the average power for this circuit. So, uh, so first we delete all these traces. So first we delete the traces. So then add trace. For now, click the AVG for average and then the power across R1 to determine the output, the average power of the R1. As we can see, it's not a sine wave, but it seems that the power uh, resonates within the range of a certain value. So we will try the measure on the last point of this graph. So you will use our cursor. And now as we can see, the measured power based on the graph here is 62.511 watts. Try to going back to our computations, the average power we can base when we're trying to solve this, we can use circuit analysis on AC circuits. So for the formula for average power is voltage in effective value of the voltage times the effective value of the current cosine theta or the phase angle of the current. So That means this is the acquired values for the voltage, the RMS value of the voltage, the RMS value of the current, 5 square root over 2 cosine 0. Since in the problem, looking back, is there is no uh, phase indicated, which means it automatically equivalent to 0. So now we can see that by computing these values, sorry for the repetition of this part, but for computation of the values, we can see that the average power is 62.5 watts, which is closer to this value of 62.511 watts. This means that uh, the graph proves that the formula we used is correct. We will replace this resistor. So first, delete the resistor and then add a new uh, component. So place this component, and this time we choose inductor. Control R to rotate. And then we will change the value of our inductor. Instead of 10 microhenries, we will use 10 millihenries. And then OK. And now we will simulate the circuit since we will find out what is the instantaneous power of the inductor and its average power. By running the Spice, it is the same Spice profile from the resistor, and now uh, we will add some traces. So add trace, first the instantaneous power, which is the WL1, then click OK. As we can see, it forms a perfect sine wave. When we noticed earlier from the resistor, the sine wave started from 0. Now we will measure its instantaneous power. So we will measure it from approximately its peak, which is around 2, 2.102 m, which is as you can see here, 47.119 watts. Based on our computation, as you can see, for the formula of power, it's current times the power. But since it is an inductor, the formula for inductor is the inductance in henries times the instantaneous current flowing across the inductor. By substituting its values, as we can see, we will integrate this equation, and after we integrate, we simplify it and resulting it to 30 pi sine squared 2 pi 60t watts. When we try to measure its peak, as we can see, it's approximately 2.0816, which is closer to the value we get here, which is 2.102 m. We will produce we will produce 47.062 watts based on our computation. But since we measure it, it's 47.119 watts. There is a difference between on the decimal, however, which implies that the values are still near or small and or comparable enough to conclude that uh, the that our calculation corresponds with the graph of the power absorbed in the inductor. Now when it comes to our average power, so we will delete this trace first, adding the trace, this time with AVG and then the power in the inductor, then click OK. As we can see, this graph is approaching to 0. So we will try to measure on the end of the graph. As we can see, the value is 8.6461 microwatts. And when we try to compute it, we can see that the R average power is 0 watts. So how does our graph produces small and our computation is 0 watts? So as we can see, cosine 90 is equal to 0 and everything multiplied to 0 is 0. So why we use cosine 90 for this particular uh, part of the problem when we try to using a circuit analysis on EC circuits, we know that the inductor is lagging or lags with 90 degrees in compared with the voltage. So it means that earlier in the resistor, since it always in phase with the voltage, we use cosine 0. But since it is an inductor and the the inductor is out of phase uh, with the voltage, so therefore we will use cosine 90. So therefore it's 0. So multiplying those three, we will produce a 0 watt. When we tried here, we measured 8.6461 micro, which is approximately equal to 0. So this means that before this 8, it means that there are 5 zeros, approximately 5 zeros, if I'm correct, before the 8. So it is comparably small or comparably equal to 0 at the power absorbed by a DC source. So we will replace this inductor by a voltage DC source. So we will delete this and place a DC source. From place Pspice component source, voltage sources, and then DC. So we will place it here and then click escape to avoid duplication. Then press W to connect the probes of this DC source and then escape. So now we will place the value of the DC source. So the default is 0 volts, but we will uh, replace it with 12 volts. Then click OK. And now we will run the simulation. So we will add the trace for instantaneous power, which is WV1. Then click OK. As we can see, the graph is inverse. So it means that in the first half, it maybe releases or dissipates the power on the DC source and then absorb it again, and the cycle continues. So when we will measure at its peak on the first half, we can see uh I think this is the peak. So in 4.1744, it measures 60 watts, negative 60 watts. So it means that it inverses the power based on the computations. When we will put it on a 4.1231 millisecond mark, it will measure at negative 59.999 watts. So this means that since it's negative, the polarity is inverse. So the values are close to each other, which proves that the output of the graph corresponds with the solution uh, used in computing its calculated values. So for the average, we will plot it again, but this time with average then from the power of the DC voltage source. As we can see, it is inversed again, but we will measure at the end like we did on earlier on other circuits. Now, as we can see, the measured the measured power rather, is negative 5.5212 microwatts, and are based on our computation and average. As we can see, uh, for solving the average current, we should integrate for the formula of power. We should integrate the uh, the current source from 0 to 1.66 to 16.67 milliseconds. By integrating this equation and simplifying it, we will produce 0.7956155,923 times negative cosine 6.28 minus negative 1. By computing this cosine, it will yield to the approximate value of 0. By multiplying those two, we will produce uh, the average current of 0 amperes. So since the formula of uh, power is V times I, which is, so we have 12 volts, which is the value of our DC source, and the value of the average current, which is 0, we will yield a 0 watt. As we can see, this value here approximately equals to 0 since this number is very, very small. So in conclusion, every element has its own way in absorb in managing their power. Some of them are absorbing the power, some of them does not absorb at all, or they just simply dissipate it, and some of them they absorb it, and then dissipates the power again. And this is for the and this is the end of this video. See you. Hope you like it and see you again next time.